Hi students, let's start with the study of the gas laws. Very simple chapter, numericals are involved. So, study of gas laws, right? There are only 7 to 8 question answers in this entire chapter, starting with the first one. All right, the first is the characteristic properties of gas or of gases. Okay, I explain this in short. I call it as a Hendel concept. Hendl. Stupid it is, but it's okay. You're gonna remember it this way. Hendel concept. H stands for high compressibility. E stands for exerts pressure in all directions. N stands for no definite shape and size. D stands for diffusibility and miscibility. And L stands for low density. Very simple, guys. So first, can I say the gaseous molecules are very much apart from each other. The force of attraction is less. The interparticle distance is more. So I can say since they are far away from each other, when you increase the pressure, E, can I say they have the scope of coming together. So they will come close and they can be compressed. Right with this? Second, they exert pressure in all the directions. Obviously, whenever a gaseous molecules or when gas molecules are stored in a container, they hit the walls of the container in all the directions. So they cannot be, they don't just exert the pressure either downwards or lateral direction. It is all the direction. Because even if you make a hole on the top, from the top, the gaseous molecules will evolve. They will liberate. They will emerge out, right? Third, they don't have a definite shape and size. They definitely take the shape and size of the container like a liquid. So whatever the container shape size is, they will definitely take the same shape and size. So no definite shape, size, they are just expand indefinitely. Diffusible. Diffusible means mixing nature. Whenever you're talking about one gas A and another gas B, you get them close to each other. Obviously, the gaseous particles are quite apart from each other, right? There is a lot of space between them. So when you get both of them close, obviously there is going to be an intermixing, okay, miscible. Miscible means a mixing nature. They can diffuse, come close, combine, right? Not chemically though sometimes, but definitely physically sure. Yep. So they are diffusible. And the last, they have low density. Obviously, the interparticle or intermolecular distance space is so vast. So obviously, if the volume increases, the density decreases. Because volume and density for a given mass of a gas are inversely proportional to each other. 5 characteristic properties of gas. All these gases, they are hit by 3 parameters always. So my second answer is about the 3 parameters. The first one, temperature. Second one, pressure. And third one, volume. So these are the 3 parameters which are important in studying a gas. Right, first, temperature. What is temperature? Can I say temperature is the indicator of the average kinetic energy of a gas. It's an indicator of the average kinetic energy of gaseous molecules. That means if there is a container, I'm heating one particular part of the container, that part will definitely be heated up more fast, right? And the other portion, the farther region, is going to be heated up less. So I can say the molecular motion of the gaseous molecules in this region where I am directly heating is bloody more. And that region, the molecular motion is less. So what I do is I say the average, the mean of all the gaseous molecules, we calculate the molecular motion. So I can say, temperature indicates the kinetic energy. More the kinetic energy, more is the temperature. Yep. Temperature is measured usually in SI unit, which we call it as Kelvin. Sometimes degree Celsius is acceptable. But in my numericals, compulsion, it has to be Kelvin. Pressure. Pressure, we have a formula, thrust upon area. I can say pressure, okay, exerted by the gaseous molecules on the walls of the container, pressure exerted by the gaseous molecules on the walls of the container, okay, is nothing but the thrust, the force acting by the gaseous molecules per unit area. You make the area 1, pressure is equal to thrust. Volume. Before that, pressure is measured in either centimeter of Hg, or you measure in millimeter of Hg, or you measure in torricelli, or you measure in atmospheric pressure. So pressure has 4 units of measurements, right? And remember, 1 atmospheric pressure is as good as 760 centimeter or 76 millimeter of Hg. Oh, I'm sorry, I wrote it the other way around. 760 millimeter or 76 centimeter of Hg. That's how the pressure can be measured as. Volume. Gases can expand indefinitely. There is no restriction to the gaseous molecules. If you, let's say this is the container and there are gaseous molecules out here, they will occupy that much space. If you expand the container, that means if the volume, if the pressure decreases, the size area has widened, the area has increased. So I can say the gaseous molecules won't be restricted to this much part. They will also rise. They will try to get separated out, spread out, occupy the entire area. So I can say volume. Gases can expand indefinitely. They can spread out through the entire volume. Right? That's volume for y'all. In volume, remember the 2 conversions. Liter is same as decimeter cube and milliliter is the same as centimeter cube. If you want to convert a liter to either a cm cube, centimeter cube, cubic centimeter or milliliter, multiply by 1000 and the vice versa way, divide by 1000. Remember this for the numericals. The next answer is about the first law, and that's going to be for y'all the Boyle's law. In Boyle's law, remember, temperature is a constant. So the first point, temperature remains same. That means one of the parameter from the 3 of them, we have kept it as a constant, and it is temperature. Boyle's law states, if the pressure increases, the volume decreases. So for a given mass of a dry gas, there should not be moisture. Then the readings will be accurate. For a given mass of a dry gas at a constant temperature, pressure and volume are inversely proportional. Pressure is inversely proportional to the volume. That means if pressure increases, then volume decreases. So I can say pressure is proportional to 1 upon V. When you convert the proportionality to equality, pressure is equals to K upon V, where I can say K is a positive constant. Some constant. Obviously, in either maths, physics or chem, if you convert a proportionality to equality, the rule is we put a constant. Cross multiply. P into V is equals to K. That means if I take a gas under two different conditions, then we have a formula P1V1 is equals to P2V2, and that answer is going to be a constant, which is K. And this is the equation which we obtain from Boyle's law. And remember, they are inversely proportional to each other. So if you happen to draw a diagram, a graph, it's a volume versus a pressure graph. Volume out here, pressure out here. As I said, as the pressure increases, the volume decreases. So whenever there is an inverse proportionality, it's always a decreasing curve, or it is always an exponential curve. It's a curve. So out here, temperature is a constant. Right, that was Boyle's law for you. More than enough, 4 pointers and a graph. Right, talking about the next law, which is Charles' law. Same pointers, let's go in the similar fashion. First, temperature was a constant. In Charles' law, I can say pressure is a constant. Second, the definition. For a given mass, I'm not writing it, please, it's getting bugging. But come on, for a given mass of a dry gas at a constant pressure, can I say temperature is directly proportional to volume. That means if temperature increases, if I'm increasing the temperature, then I can say the molecules will get heated up. If the molecules are heated up, yeah, the kinetic energy increases. Kinetic energy increases, they start running here and there. Oh my God, oh my God. And then the molecular motion increases. Molecular motion increases, can I say the volume increases? Oh, come on. The gases, they start running here and there, everywhere. That's like temperature and volume, right? So if temperature increases, the volume has to increase. Okay, the third pointer. So temperature directly proportional to volume. If temperature increases, yep, then volume increases. If temperature decreases, oh God, then volume also decreases. Okay. So from here you can comment in terms of a mathematical notation. Volume is proportional to temperature. When you convert the proportionality to equality, we put a K, a constant. K is a positive constant. So V upon T is equal to K. If I'm talking about two cases, okay, we get V1 upon T1 is equal to V2 upon T2 is equals to K. And these are the cases, the conditions for the which law? The Charles law. Alright, and if you draw a graph of Charles law, always remember it's a volume versus temperature. As the temperature increases, volume also increases when pressure is kept a constant. A straight graph. So guys, what I'm expecting you all to do is go through this, and we will still some couple of things left to be taught out. One of them is the gas equation. Second is about the absolute zero and the absolute scale, and some portions for STP, NTP. And then we are going to jump, okay, hit the numericals. 2 numericals on Boyle, 2 on gas equation, and 2 on Charles. Yep. Talking about the gas equation, the last part. Now, what we did was, we first kept temperature constant. We studied about the pressure and volume. Then, we kept pressure constant. We studied about the temperature and the volume. Now, no keeping constants, man, no keeping constants. We are going to change both. We're going to change the temperature, we're going to change the pressure, and because of the changes of both, we're going to study about the behavior. We're going to study about the nature of the gaseous molecules in terms of volume. So I can say change both. Change the temperature and change the pressure, and let's study the effect on the volume, and that is given by the gas equation. So for a gas equation, remember one thing. First, you combine the Boyles and the Charles law, right? We know, according to the Boyles law, forget about the temperature being constant. Don't we know that volume and pressure are inversely proportional? So I can say pressure is inversely proportional to volume, or volume is inversely proportional to pressure. And from the Charles law, and temperature and volume are directly proportional. Volume is proportional to temperature. So now what you're going to do is combine both of them. I can say volume is proportional to temperature upon pressure. Nope. Wait. Cross multiply. PV proportional to T. Get the proportionality to equality, KT. So PV upon T is equals to K. That's the gas equation for y'all. And for two conditions, what you did was I just said volume is together on the top, temperature at the top, pressure in the denominator at the bottom. You cross multiply, you put an arbitrary constant K, get the T down. PV upon T is equal to K. So if there are two equations or two conditions, P1 V1 upon T1 is equals to P2 V2 upon T2. That's the gas equation under two cases, which we'll be using for numericals. Alright. The next part of the answer is about the absolute zero. And the absolute scale. Now it is said that on this earth, the minimum temperature which was achievable, which was attainable, which the scientists or whoever you can say, they could reach is minus 273 degrees Celsius. And they actually could get this temperature for a small portion of time. It was very difficult to sustain such a small temperature for a longer period of time. But yes, it did reach minus 273 degrees Celsius, but for a fraction of a time, right? So I can say, if you make a graph, do we know this is 0 degrees Celsius in terms of degrees Celsius? This is minus 1, minus 2. It's a negative x-axis, students, and it goes on up till minus 273 degrees Celsius. What happened is, this was temperature, volume. Yeah, what happened, as I said, was this was a gas at volume V0 or V. As the temperature was reduced, the gaseous molecules start coming close to each other. They started getting compressed. Small. Compression. The area is less. Volume is less. So the volume started decreasing. Straight line actually. And eventually, it's a straight line. I'm sorry, okay. What happens is eventually, as the volume decreased, at a point of time, it vanished. Well, what vanished there? The gaseous molecules vanished. The molecular motion stopped. We say that the molecular motion, gas molecules cease to flow. Oh, come on, bloody gas molecules don't flow only. Now, how is that possible? Or is it very difficult? Because you are just seeing a standstill. A standstill means the gaseous molecules, which we say are always moving, suddenly a stop. A gaseous molecule comes to a stop. I can't see this gaseous molecule moving. Guys, that's difficult to analyze. That's difficult to digest. I can say that this happens at absolute zero. What is this absolute? Complete. It's over. It's not less than that, man. So I can say at this temperature, the molecular motion stops, volume becomes almost zero, right? It's an imaginary condition, like a vacuum. Alright, and this temperature is called absolute zero, which we also call it as 0 Kelvin. It is not OK, it is 0 Kelvin. So remember, 0 Kelvin is as good as minus 273 degrees Celsius, or 273 Kelvin is equal to 0 degrees Celsius. Okay, remember these values. So for every 1 degree Celsius rise, there will be 1 Kelvin rise. 2 degrees rise, 2 Kelvin rise. The Celsius and the degrees, the rise and the fall is proportional, right? But the start goes this way. So I can say a 0 Kelvin is like absolute. You cannot have a negative Kelvin. You cannot have a temperature less than 0 Kelvin. So can I say a Kelvin scale is always a positive scale? Alright, the last portion, if you come across for the numericals, if you come across the words like STP, standard temperature and pressure, remember two things. First, the temperature is always 0 degrees Celsius, which is 273 Kelvin. And second, the pressure is always 76 centimeter of mercury or 760 millimeter of mercury. These are going to be the fixed values. So henceforth, when you come across this word, you close your eyes, enjoy the moment, because you know these two things are going to be fixed. Right? Go through this, and that was the end of my theoretical part in gas laws. We're going to attack two numericals on each of them.